All right, so in this section, I will review rotational motion. And obviously, this is a really big chapter. This was chapter 7 for us, and it covers so many different avenues. So I'll try to review most of the basics, but the bottom line is this is a chapter we'll have to practice a lot. So don't get discouraged, just keep working at it. But hopefully this helps you maybe get started on some of those questions. So let's begin with a couple of the relationships. Now, these are relationships that are not on our equation sheet, but are very helpful for translating to and from angular and linear sets of motion. So the first of the helpful equations for us is actually just the definition of what a radian is. So this is actually just redefining what a radian is. It's just kind of rewriting that equation. But what this is showing me is that the linear distance or displacement relates to the angular displacement times the radius, right? So if I want to find out how far around the circle I've gone, so for example here, if I want to find out what this distance from here to here is, I need to know what's the radius of that circle and what's the angle that I've covered, and that will provide me this relationship. It is worth noting that this angle needs to be measured in radians. We have a very similar definition then to this, which makes sense because if I were to simply take this equation and were to take the change in this equation divided by time, so in other words, if I take the change in x divided by the change in time, and I do r and then the change in theta divided by the change in time, it gives me my second relationship, which is v equals r times omega. So again, it just follows the same pattern, right? Linear velocity or tangential velocity equals the radius times omega. So this is helpful if I want you to find maybe the tangential velocity, a certain radius from the center of the circle, and I know the angular velocity of the disk as it's rotating. That's what this can help me do. And then we get to the accelerations. Now the accelerations, we have to be careful. If you've reviewed uniform circular motion or circular motion at all, we know that anytime we move in a circle, we have to have a centripetal acceleration, right? We have to have that because the direction is changing. So no matter what, I have to have a centripetal acceleration. Now, if I am also accelerating around the circle and picking up speed or slowing down, then I have a tangential acceleration as well. And the tangential acceleration relates to r times alpha. Alpha being our angular acceleration, and then again tangential being how fast are we accelerating around the circle. So theta, omega, and alpha, those are our angular measurements, right? Those all represent how far we've gone or how fast we've gone or what's our acceleration in terms of radians, and then our standard unit for time, as always, is seconds. A couple key concepts that then come with these. One big thing to make sure we know is as an object is rotating, assuming that that is a rigid object, meaning it doesn't distort or bend or do anything kind of goofy as it's rotating. So if this object is rotating and it's all rotating together, then every single point on that object, it doesn't matter where that point is, every single point should rotate with the exact same angular measurements, right, as any other point on there. So angular measurements are always going to be the same as long as it's a rigid object that's rotating together. So they all cover the same angle in the same amount of time, right? So whether this is 60 degrees or whatever it may be, they all cover that exact same angle. They all accelerate at the same angular rate, so they all have the same alpha, they all have the same omega, they all have the same theta, right? As they're rotating, they have to because they're covering the exact same angle. However, the linear or the tangential measurements, as we can see based on these three relationships over here, if they have the same theta, the same omega, the same alpha, then their distance, their linear velocity, their tangential acceleration will all depend on how far away they are from the center of the circle. That also makes sense, right? If I've got a circle here, this point is only needing to make a circumference of that far in one revolution, whereas if I chose a point towards the outer edge of the disk, it needs to make a much larger circumference in the exact same amount of time. So obviously it has to be going much faster linearly in order to make up that difference, right? I think we agree that if I took those two distances and made them into straight line distances, right, the larger one on the outside would be obviously much longer. And so it has to go a lot further in the same amount of time, therefore it must be going faster linearly. So again, very, very big concepts for us early on in that section. The other relationships that then alpha leads to. So alpha represents, again, our angular acceleration, right? And if it's a constant angular acceleration, then it follows the exact same pattern as when we had a constant linear acceleration, meaning all of the kinematics equations that we still know are still true. They just take their angular formats, right? Their angular versions. So instead of VOTAT, right, we know that we've had VOTAT. We've worked with this a lot throughout the year. But instead of that, we now have what I like to refer to as WOTAT, or ROTALFAT, however you prefer, right? But that's the angular equivalent to the velocities for the linear velocity as well, right? So the angular version of our first acceleration, our first kinematics equation, right? And truly, this is just the definition of angular acceleration, right? What is acceleration defined as? Well, acceleration is defined as a change in velocity over a change in time. So angular acceleration is a change in angular velocity over time. If you simply rearrange this equation, you get the first of our three kinematics. The other two, we won't necessarily worry about proving these right now, but again, we should be familiar with, right, our other variations for our angular kinematics. The biggest concept that comes with these three equations right here, well, I guess these three, right, those and those two, right? The biggest concept that comes with these is the fact that when can I and can I not use these, right? We can only use these if the object is accelerating angularly, which means I would not use it if it's uniform circular motion, because if it's uniform circular motion, it is not speeding up as it rotates, and therefore it is not accelerating angularly. So if it's uniform, I don't use these three, right? If it is accelerating, so if it is either speeding up or slowing down while it's rotating, that is when I would use these. And it does technically have to be a constant acceleration as well. Now, in Physics 1, we don't typically see non-constant accelerations, but it is something we want to make sure we're paying attention to in terms of when do I use these and when do I not. But yeah, make sure we're comfortable with those ideas, right? So then the next kind of natural progression with this all is what causes an acceleration, right? We know with linear measurements, in order to have a linear acceleration, we have to have a force which then causes, right? So if I have a force, I have an acceleration, right? If the net force is 0, then that tells me that the linear acceleration is 0. Well, we actually see the same pattern emerge again with our rotational measurements. We once again just have to be able to translate between linear and angular. So what is the angular version of force? Well, for lack of a better term, right, the angular version of force is torque. And what I mean by that is torque relates to the moment of inertia, which kind of acts like my angular version of mass, and then times alpha, which is my angular version of acceleration. We see the exact same concepts emerge with torque. If the net torque is 0, then that tells me that the angular acceleration better be 0, which means that the object is either not rotating at all and it's at rest, or that it's rotating at a constant angular velocity and a constant linear velocity as well, right? So we've seen torque. Torque takes us back to like the tension questions we've seen before, where maybe you have a tension here, right? So you know that the torque caused by the beam needs to be equal and opposite to the torque caused by the tension. And we know that those two torques would have to be equal and opposite because the beam is not moving, and therefore it is in equilibrium. And if it's in equilibrium, the net torque is 0. And the only way the net torque is 0 is if those two torques are in fact equal and opposite. So then if we break this down a little bit more, a couple different ways to work with this, right? So one, we need to realize that to calculate torque, so if I did want to find these two torques individually, to calculate torque, I simply do force times the radius. But we do have to keep in mind that we only want the force that is perpendicular to the radius, right? So we only want the force that is perpendicular to the radius. I believe on our equation sheet, they give us the format that looks something like this, indicating that we only want the component that is making a vertical or a perpendicular component with our radius. So for example, the tension here, right? The tension is actually pulling off at an angle, but we only want the component of that tension that is perpendicular to the radius. We do not want the entire tension as that's pulling off, right? So we need to be comfortable with torque. It's just force times distance. And again, the big idea, the thing that we really need to walk away with is when should the net torque be 0, right, if the object's not accelerating, and then finding a way to balance those torques. Or what happens if the net torque isn't 0, right? Well, if the net torque isn't 0, then maybe I'm using this relationship. And maybe I'm relating that and setting that up with either kinematics or other forces that are at play. So that's something else to keep in mind. While we're here, we might as well define what I is. So I is the moment of inertia. And again, the moment of inertia, what does that actually mean? Well, that's just the tendency of how easy or difficult it is to rotate something, right? So if something has a really low moment of inertia, it means it's really easy to cause that to change its rotational motion. It's really easy to accelerate it angularly, which makes sense based on this equation, right? If something has a really high moment of inertia, it's really tough to change its state of motion. So we need to be comfortable with that idea. The basic definition for the moment of inertia is simply mr squared. And this works great if we just have a single mass. So if I have a single mass here and it's being swung around in a circle or whatever it may be, right? If I ask you what's the moment of inertia of that mass around the center of the circle, we would simply take the entire mass of that object, we would take the radius, and we would do mr squared, and that would define the moment of inertia for that circle itself, or for that mass itself, right? It is worth noting what tendencies tend to make the moment of inertia higher or lower, right? So if I wanted to increase the moment of inertia of the picture I just showed you, one way to do that would be either make the mass bigger or make the radius bigger, right? If I wanted to decrease the moment of inertia, again, the exact opposite, either make the mass smaller or decrease the radius. We also saw a variety of different shapes. We saw like the moment of inertia of a sphere, we saw the moment of inertia of a cylinder, and several other shapes. You are not expected to memorize the coefficients for those different shapes. So for a sphere, it's 2/5. For a cylinder, it's 1/2. For a hoop, now for a hoop, we probably should be able to justify as to why it is just 1 mr squared, right? And that's because all of the mass is the full distance away. That makes sense. Okay, but again, with the other two, you really don't need to try to memorize these. What you should be able to do is you should be able to explain why they do have lower moments of inertia than, say, something like the hoop, right? So the cylinder and the sphere both have a lower moment of inertia than the hoop because they have more mass concentrated towards the center of the object, right? So if the sphere is rotating around itself, it's got a lot more mass concentrated towards the center, and therefore not every mass is the full radius away, and therefore rather than just using mr squared, I'm using 2/5. Again, if they want us to use that equation, they will define that for us. Otherwise, conceptually, you just need to know why it would have a lower moment of inertia versus the others. But yeah, just make sure we're comfortable with that idea, and then hopefully nothing too crazy from that. Right. In terms of being able to work with moment of inertia, it is important we also know when we use these special equations, should they pop up. Right? We only use those equations if the object is rotating around itself. So if you have an object that's rolling down a ramp, it is rolling around its own center of mass. That would be when I'm using these three equations. If I have a sphere and that sphere is being swung around a string, I don't care if it's a sphere or a block or a disk or whatever it may be, because if the entire mass of the sphere is the full distance away, I simply use mr squared for that scenario. So it is also worth noting that we need to be comfortable of when we should use the special variations of this equation, right, and when we should use just mr squared. Again, if you're ever in doubt, just stick with mr squared. But if the object's rolling around itself, that's when we should be thinking about the other coefficients as well. Right. So making sure we're comfortable with that idea, right? Using torque to find the either balanced torques and find out that it's in equilibrium, or setting up a net torque. We've seen a variety of examples. Again, this is going to be a big section to just practice, and make sure we've seen kind of a number of different avenues with it. A few other things, though, to tie up here as we're wrapping down, excuse the bad pun, right, winding down the rotational motion here, right? But in other words, let's look at a couple other concepts as we get going. So we also have rotational kinetic energy, which is our main form of rotational energy, right? So rotational kinetic energy, which we know is 1/2 I omega squared. Once again, that is defined for us on our equation sheet. We just have to be comfortable using it. And rotational kinetic energy is the energy associated with an object as it is rolling. So a few key ideas with this is we need to know when we use it, right? Well, we use this when it says the object is rolling, or if it says something like it is slipping, or excuse me, it is not slipping, right? So it is rolling without slipping. So if they ever say the expression without slipping, that is indicating that rather than sliding down the ramp or sliding across the surface, that it is in fact rolling. So sometimes key phrases like that we definitely need to be comfortable with. The other interesting thing to think about with rotational kinetic energy is, where is this coming from? So if I have an object that is rolling across the floor, what's causing it to roll? Well, if you think about the forces acting on this object, the force of gravity would act from the center of mass and it'd be pulling straight down. The normal force would act upward from the floor and again would be pushing straight up. Those two forces obviously most of the time are going to be equal and opposite unless we're also pushing up or pulling up or pushing down on this object, right? So what force is causing it to roll? Well, the key force that causes it to roll is actually friction. And so friction is the force that's, if you notice, perpendicular to the radius, and therefore it's producing a torque, and therefore it is what's causing us to roll and to accelerate. So if they ever ask us, hey, what's causing the rotational energy, or what's causing an object to roll, it's actually friction that requires it or causes it to roll. And so when an object's rolling, friction doesn't necessarily, quote unquote, waste energy. Instead, the work done by friction is simply what leads us to our rotational kinetic energy. Now, there are a couple different variations of friction, so that's not always the case. But in this case, where friction is parallel to the surface, if it's rolling without slipping, then friction is often the agent that's causing it to gain its rotational kinetic energy. Another concept that comes up with kinetic energy and rotational kinetic energy is, once again, work. If I ask you to find the work done on something, right, one of the easiest ways to find the work done is to simply find the change in energy. So if I have maybe a merry-go-round and it's starting at rest, and then I have a moment later, right, so sometime later that merry-go-round is now rotating, and I say, well, how much work was done on that merry-go-round? Well, the easiest way to probably find it is simply find the kinetic energy beforehand, which if it wasn't moving would be 0, and then find the rotational kinetic energy afterwards, right, and that would be how much energy it's gained, and therefore that would be how much work we have done, right? So those are the types of relationships, those are the types of connections we definitely need to be able to make in terms of rotational kinetic energy and work. Otherwise, we've seen the common example where if I have a mass rolling down the ramp, so it's rolling without slipping, it starts with potential energy. As it rolls down the ramp, that energy goes to both linear or translational kinetic energy and rotational energy, right? So we know that some of the potential energy is going to go to each of those, right? This is a key question because we've seen it a lot before, right? And in this question, we know that if something has a lower moment of inertia, then it means it's going to have less required rotational energy, and therefore it would have more translational or linear energy, and therefore it would be moving faster, and therefore its time would be less and it would finish first, right? So once again, we've seen that type of question before. We definitely want to make sure we're comfortable with that relationship should that pop up on us as well, right? And then the last couple ideas that come into play. So if we go back to momentum, like linear momentum. So linear momentum is defined as, right, the change in momentum is defined as the mass times the change in velocity, right? Or momentum on its own is just mass times the velocity. Well, we see the angular version of that too. We use the letter L for our angular momentum, and the angular version of mass, again, is my moment of inertia. The angular version for V is omega, right? So we've got our angular momentum as well. So angular momentum, right, represents very similar to what it would be for linear momentum, I times omega. Easy enough to find on its own. The big question is, when should angular momentum be conserved and when should it not be conserved? Well, again, let's take the parallels to our linear system first. If there is an outside force, then we can use F delta T equals delta P. If there is an outside force that is not 0 and it's acting for a certain period of time, then what that tells me is the momentum should change. So if there's an outside force, momentum should not be conserved, it should change. We see the exact same relationship pop up. Oops, excuse me, I wrote that wrong. We see the exact same relationship pop up for angular momentum. If there is an outside torque acting for a period of time, then the angular momentum should change. Linearly speaking, if the net force is 0, then momentum should be conserved, right? So my initial momentum should be conserved and equal to my final momentum. Same idea. If the net torque is 0, then the angular momentum should be equal to the final angular momentum. This is a huge relationship force. This is one that I've actually seen pop up a lot. And it's a big idea, but the toughest part is identifying when is there a net torque and when is there not, right? So take it back to what we did for linear momentum, and a lot of times in most of our collisions, so for example, if I have maybe a wheel that's rotating, and then all of a sudden I drop a blob of clay onto that wheel, it's like a collision. It's like a perfectly inelastic collision where the two objects stick together. Even though there are some equal and opposite forces acting on the wheel and the clay, there are no outside forces acting on the whole system. And because there are no outside forces acting on the system, there really shouldn't be any outside torques acting on the system either, right? And so if there's no outside torque, we know that the angular momentum should be conserved, and that in fact gives us the route that we need to solve an example like this. And there's 100 of examples that we'll see on these types of questions. And like I said, this is a big chapter. I know this is a long video. I don't want to drone on and on and on, right? So go back through, review these concepts, but then, like I said, this is a big section to maybe make sure, before you try any more examples, sit down and write yourself your own list of these and make sure that you know how to solve these before you try to work too many examples. If you feel like you can get through most of the content of this video without needing to watch the video, then you're probably ready to do a lot of the examples. If you feel like you struggle to do this on your own, then you probably need to maybe run through the video a couple more times and practice just the key concepts before you actually start to practice the examples. But anyway, practice this section hard and let me know if you have any questions as you go through it.